So we're going to be looking at three different methods for solving an exponential equation. One of them is the algebraic method, which you need to know how to do for sure. The other two methods are kind of cheating on your calculator by either looking at your tables or guess and check or solving graphically. And I think some of those methods are a little clunky. They're more work than it needs to be. The types of exponential equations we're going to be solving today are very specific, but before we get to the specificity of those equations, let's talk about what an exponential equation is. An exponential equation, well, let's back up. What's an equation that you would ever be asked to solve? What does that mean? It means that there's some unknown in the equation that you have to rearrange the equation for. That's what it means to solve an equation. An exponential equation has the unknown as part of the exponent. So just put your calculators down for a second, please, and pay attention. We have 2 to the x equals 32. That's not a difficult equation to solve. And I know what some of you were doing. You were trying to figure out what x was, and it turns out x is 5. Because you can try different numbers for x, and you can discover that, well, 2 to the 1 is 2, 2 to the 2 is 4, multiplied by 2 again is 8, multiplied by 2 again is 16. I guess we would have to have 2 multiplied by itself 5 times to get 32. And we're going to be looking at how we know that in a little bit, but the bottom line is that's what an exponential equation is. So the first set of examples are going to be solving exponential equations using a common base. I want you to notice that there's an x in the exponent of this equation, in 2 exponents, but the base is the same. There's a base 7 on the left, there's a base 7 on the right, so we say that's a common base. Actually, you know what? Before I do this one, I want to give you an even simpler equation. I want everybody to solve this equation. I want you to think about what I've just written, and I want you to figure out for me what x is. There's no real work involved here, is there? Who can tell me what x is? Makai? Sorry? 7. I mean, if I'm saying 8 to the x is equal to 8 to the 7, it makes sense that since the base is the same on both sides, that whatever the exponent is on both sides must be the same. The only way I can make that into a true statement is to have the same exponent because the bases are the same. So what we do here is you simply say x equals 7 by comparison. I want to really stress something here. We did not, in going from here to here, cancel the 8s somehow. You're not dividing both sides by 8 or anything like that. You're simply saying if the bases are the same, the exponents must be the same. Well, that means in question A that if 7 to the 4x minus 5 is equal to 7 to the 2x plus 3, then 4x minus 5 must equal 2x plus 3. And we have gone from a Math 30 equation very quickly down to a grade 9 or grade 8 or maybe even grade 7 equation where you're trying to solve this for x. I would subtract 2x from both sides and get 2x. I would add 5 to both sides and get 8. And when you divide both sides of this equation by 2, you get x equals 4. And if you truly understand what we've just done here, it's almost childlike in its simplicity. We're just saying that if you put 4 in for x, those 2 exponents will be the same. And if those 2 exponents are the same, then 7 raised to that exponent on the left and 7 raised to the same exponent on the right will give you the same number. By the way, if you do put 4 up here, you're going to get 11. If you put 4 here, you're going to get 11 for an exponent. So we would end up with 7 to the 11 equals 7 to the 11. So what about this? We have 3 to the 3x plus 1 equals 81. 81, by the way, is a base in this exponential expression. I can write 81 as 81 to the 1. So 81 is a base and 3 is a base, but they are not the same base. So I cannot take the two exponents and make them equal to each other. But 81 can be written in base 3. We can take the number 81 and figure out what it is equal to in base 3. I hope when you see 81, you see the number 9 times 9. I hope, if you know your times tables. And 9 is 3 times 3, and the other 9 is 3 times 3. So these are numbers you'll get more and more familiar with, but if you take 3 raised to the power of 4, you'll get 81. Because if you look up here, 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81. So now we can rewrite this equation as 3 raised to the 3x plus 1 equals 3 raised to the 4. Okay, now we have a common base. The base is 3. You know, essentially what I'm telling you is that if you have that, then you automatically have that. Well, the shape has changed a bit, but you get my drift. If the bases are the same, you can ignore the bases and set the exponents equal to each other, regardless of what the exponents are. So 3x plus 1 equals 4. You know, with a little bit of prodding, I could get a grade 3 or 4 student to figure out what x is if they understood the concept of x. What number do you multiply by 3 and add 1 to get 4? The answer is going to be 1, but we have an algebraic way of solving it. We subtract 1 from both sides and divide both sides by 3. So you get x equals 1. You might want to make a note to yourself, there's no extraneous roots in exponential equations yet. There might be some weird variations later on. 36 raised to the 2 minus 3x equals 216 raised to the x. So apparently, there's a common base that I can express 36 in and 216 in. So if you look at the previous example, 81 could have been written as a power of base 3. Maybe 216 can be written as a power of 36. I don't know. Is 36 squared 216? If it is, then we can write 216 as 36 squared and have a common base. But it's not. So that means there must be another base smaller than 36 that they can both be written as. Well, the only way I can write 36 as a power would be to write it as 6 squared. That's the only way I can write 36 as a power, other than 36 to the 1. And that means, so right now over here, I'm just kind of playing around on my calculator or in my head, and I'm going, well, Jesus, is 216 actually 6 raised to an exponent? And I think it is. I think it's 6 cubed, isn't it? So that thing that a couple of you were doing on your calculator when I wrote 2 to the x equals 32, that's kind of what you're doing here just to find the exponent. So the 216 is going to be 6 cubed, but what do we do about this other stuff? It's 36 raised to the 2 minus 3x, which means it's 6 squared raised to the 2 minus 3x. And that set of brackets it's not optional. You need that set of brackets. And it's 216 raised to the x, but 216 is 6 cubed, and we have to raise that to the x. And now what we need to do is go back to, I guess grade 9 is where you're first introduced to this, which is if you have, I'm going to use different letters here, a to the b to the c, that's equal to a to the product of b times c. This is called a power of a power. It means that you have an exponential expression raised to another power, and you multiply the two exponents. So I'm going to get on the right-hand side 6 to the 3x, And on the left-hand side, I'm going to get 6 to the 2 times 2 minus 3x. And I have no problem at all with you writing instead 4 minus 6x at this stage. I'm just doing it in steps to show people what's going on. Can we drop the bases at this point? Yes. We can drop the bases because they're the same base. If I have 6 raised to one exponent equals 6 raised to another exponent, then those two exponents have to, in fact, be the same. They may look different because there's an x involved, but they have to be the same. Where you multiply that 2 through is entirely up to you. You could have multiplied it through right at the beginning. If I do expand this by distributing that 2, I get 4 minus 6x equals 3x. I can add 6x to both sides and get 9x equals, that's a 4. It looks like a y, but it's a 4, which means x equals 4 divided by 9. And, you know, we could certainly verify that. I don't think we really have to. Correct me if I'm wrong, the left-hand side was 6 to the 2 minus 3x. Okay. So 4 divided by 9. There's my x. 2 minus 3 times that. 6 raised to that. This is the left-hand side when x is 4/9. The right-hand side was 216 to the x, which would be 216 raised to, in brackets, 4 divided by 9. I need the brackets because if I go raised to the 4 divided by 9 without brackets, if I enter this, my calculator will do this, which is not what I want. I need that set of brackets around there. Anyway, whoa. I didn't get the same number, did I? Oh, it was not 6. It was 36 raised to that. So I'm going to have to redo that calculation. This is x. I need to take 2 minus 3 times that. This is the exponent on the left side. I need to take 36 raised to that, which gives me that 10.9. It works. All right. Let's try this one. 5 to the x equals 625 root 5. Clearly, well, I don't know. To me, it's obvious. The common base, if there is one, has to be 5. Because the left, forgetting about the right-hand side, if I'm saying you can write this as a common base, and on the left-hand side the base is 5, there's no other way to write 5. I can't write 5 as something squared or something cubed. Not without introducing fractional exponents. So that means what I'm interested in knowing is, I'm going to have a base 5. What is 625 in base 5? What number do I raise 5 to get 625? And I want to say 4. And you'll get more used to these, but you can always rely on your calculator to find out. This is 4. So we're going to have 5 to the x equals 5 to the 4 multiplied by root 5. There's a product of these two things. Now, what is root 5? 5 to some exponent equals root 5. And this isn't a guess and check game on your calculator. You need to know that exponent is a half. You need to know that a square root of a number is the equivalent to raising that number to an exponent of 1/2. You learned this in, I think, grade 10. You might even remember that sometimes, it probably happens more in my physics class, but some of you have physics with me, I need to take a square root of a number, and sometimes I'll just do this. It's probably just as many keystrokes, but to me it's just cleaner. I don't know why. So then we have times 5 to the 1/2, and now with this, 5 to the 4 multiplied by 5 to the half, we're going to get 5 to the 9/2. Now, why? The reason why is that back in grade 9, I suppose it is, you learned that if you have a to the b multiplied by a to the c, in other words, you're multiplying two powers that have the same base, you add the exponents. You get a to the b plus c. This becomes more obvious, I suppose, if I gave you x squared times x cubed. It gives you x to the 5. Because x squared is x times x. X cubed is x times x times x. So x squared times x cubed is x times x times x times x times x, which is x to the 5. You add the exponents, but the base stays the same. So what I've done is I've added 4 plus a half. In fact, maybe I should write that in case you want to include it in your notes. I think everybody in the room would get this correct. I think if I said, what is x squared times x cubed, everybody writes x to the 5. But occasionally, when the base is a number, people make the mistake of putting 25 for the base. Because your brain sees 5 times 5. You go, oh, 25. But the base remains the same. When you add the exponents, the base remains the same. So now we have 5 to the x equals 5 to the 4 plus a half, which means x equals 4 plus a half, which is 4.5 or 9/2. Any questions with that example? All right. Solve for x using systematic trial or systematic trial and error. This is something that I'm including because your textbook doesn't, and it's not bad. It's for a student who's really struggling, they might find this useful, but I find it very clunky. What you're doing is using trial and error. So before you get to your calculator, just look up here. We can use trial and error here, but I want to be a little more sophisticated than just putting 3 raised to some number from the home screen. I know, by the way, that 3 squared is 9 and 3 cubed is 27. So if I want to raise 3 to a number to get 25.8, I know that number is going to be between 2 and 3, and it's probably going to be closer to 3. I don't want to be plunking around on my calculator here. I think the best thing to do is to put this in for y. We're not going to be looking at the graph. We're going to be looking at the table. So we're going to put 3 raised to the x in here. I've already established that I like the way this works. It's just a clunky method. We've already established that x must be between 2 and 3. So what I can do is set up my table, second window, to start at 2 and go up by a 10th. So it's going to generate 3 to the x values for x equals 2, 2.1, 2.2, 2.3, 2.4, etc. And I go to my table, and I'm looking for 25.9 for y. And what I've established now is that since 3 to the 2.9 is less than 25.8, and 3 to the 3 is more than 25.8, the answer must be between 2.9 and 3. Does that logic make sense to you? So I'm going to readjust my table. I'm going to start at 2.9, but I'm going to go up not by 0.1 this time, not by a 10th. I'm going to go up by a 100th. So I'm zeroing in, I'm zooming in on the answer somehow using my table. And, you know, you don't actually have to do this. You can follow along, or you can do it if you want. But I think it's more important that you understand what we're doing as opposed to having to actually do it. It should make sense to you. I can see here that when I use x equals 2.95, I don't get a number that's 25.8, I get a number that's less than 25.8. When I use 2.96, I get a number that's more than 25.8. So I think you know where this is going. I'm going to start at 2.95 and go up by 1,000th. And this is what I mean by clunky. I mean, I really wish I could just show you how to algebraically find it. Anyway, because it's really simple. Well, it's a simple process. I mean, I would say it's 2.959. Very close. You're never going to get an exact value here. If you had lots of time on your hands, then you could figure out what the answer is to more decimals. And if you did that, you would discover that it's actually, and don't worry about what I'm doing, you would actually discover that it's 2.958618364. Don't try to figure out what those keystrokes are. I can demonstrate this to you, 3 raised to that answer. And it doesn't just give kind of close to 25.8, it gives exactly 25.8. So that's one way you can get the answer here. The answer is about 2.96. Liam? We will do that. Yeah. I don't know if we'll do it with this exact one, but we will do it. The reason I don't really like the graphing, by the way, is sometimes the window settings get challenging. Okay, and we'll encounter that. So the answer is about 2.96. X equals 2.96. Oh, I neglected to say, I hope you understand that 25.8 and 3 cannot be written with the same base. Right? It can't be done. 12 equals 1.5 raised to the x minus 8. So we can put 1.5 raised to, in brackets, x minus 8. I really have no idea what kind of domain for x is suitable here. So what I might recommend is going to your window setting and starting at 0 and going up by 1. And we can scroll up and down that table all we want. I am looking for this expression equaling 12, so clearly it's going to be some larger number. There we go. It's between 14 and 15. So let me start at 14 and go up by 0.1. I want this to be equal to 12. It's looking like it's between 14.1 and 14.2. Let's just go to one more decimal place and then call it quits. Let's start at 14.1 and go up by 0.01. Remember, I'm looking for 12. Man, that's pretty close, 12.007. So we can say x equals approximately 14.13. At some point, this is an approximate value. It turns out it's an irrational number. Same as the answer to the previous question. Is this B on yours? Okay. At some point, you will learn how to solve this algebraically. To get a more precise answer. Okay. But that's a few lessons away. Now, what if we want to do it graphically? We could go back and do those ones graphically, as Liam pointed out. But let's take a look at this next one. 12 equals 2/3 raised to the x over 4. So we're going to enter in the two sides of the equation. Left side I'm just going to use as y1. And right side is 2/3. I need the base in its own set of brackets, otherwise I might only be raising part of the base to the exponent. And I also need the exponent in its own set of brackets. So before we look at the window, well, let's go to the window settings and let's adjust our y. I think it's reasonable to say we have to go up past 12 because we want to see y equals 12. Now, you should know that this graph here will look in general like that, because the base is 2/3, which is a base less than 1. It's between 0 and 1, so it's a declining or decreasing exponential function. Which means, by the way, that it's probably going to intersect with this graph up higher somewhere. Which means it looks like I'm going to be looking at negative numbers. So I have to use a little bit of knowledge here. I suppose if I just went zooms, was that me? No. I suppose if I just went zoom standard and crossed my fingers, it would work. But I'm not going to. I'm going to go from -10 to 10. I don't think I need to go to 10. I'm pretty sure the answer is going to be a negative number. And I graph. There's my 12. Oh, yeah. I got to go to a big negative number, don't I? I want to see where these are going to intersect, and they intersect far to the left. I'm going to go -60. I'm sure that's enough. Yep. So I'm looking at intersect. You can get past that appropriate window setting, then you're fine. So the answer is -24.5. When you take a look at 75 raised to the 2x minus 3, 75 is a huge base. It's going to be growing exponentially quite rapidly. In other words, it's going to be very steep. Very steep. If I look at 2.5 times 3 to the x, the base is 3, so it's not growing as rapidly. That 2.5 is, however, increasing the rate slightly. And when you take a look at it, you can see that the graphs are getting closer together up top somewhere. I believe that you can probably find the point of intersection from here because you're looking only at that domain of x values where they're going to intersect. But if you want to see that point of intersection, then you need to look up higher. And I'm going to go up to 50. I don't know if that's going to be enough or not. So x is equal to 1.84, approximately. All right, let's take a look at the next little section here. We're going to be talking about compound interest. When you invest money, if you're investing it wisely, the interest you earn is compounded. And you've probably heard of compound interest. What that means is that when you put money into the account, you get a certain percentage of that money that gets added onto your account. And the next time they calculate the percentage, they use that new amount as a base amount, which means you're getting interest on interest. It's a type of exponential growth. And when you solve finance problems in Math 30, you're going to solve them using this formula. Okay. So let's take a look at this example. Jerry invests $10,000 into an account, and this is how you would see it on an exam. You would see 8% per annum and in this case for Jerry it's compounded annually. What does that mean? It means that in Jerry's case, if he invests the money, say, on January 1st, that $10,000 will sit in that account all year, and then at the end of the year, they add on 8%. Okay? And then that new total sits in that account for the whole second year, and at the end of the second year, they add on 8% of that. How much is in the account after 14 years? Well, we're using y equals a times b to the t over p. A is the original amount. B will be 1.08. Does that make sense to you why B is 1.08? We're adding 8%. Excuse me. And the period of time is 1 year. So when we put those into this formula, we get y, which is Jerry's money, equals 10,000 times 1.08 raised to the t over 1. And we don't need to put over 1. You could just put raised to the t. How much is in the account after 14 years means this. When t is 14, what is y? So it's just a matter of you putting 14 in for t and solving for y. Which I don't even know if I should say solving. Y equals 10,000 times 1.08 raised to the 14. So $29,371. You getting the same number? Okay. Now there were actually two questions asked. How much is in the account after 14 years? That's that $29,371. 0.94. How much interest is earned? Well, this isn't a complicated calculation. If he put $10,000 into the account and he now has $29,000, then to find the interest earned, you would subtract those two numbers. So the interest earned is $19,371 and 94 cents. You okay with example 4? Okay, example 5. Elaine also invests $10,000 into an account. Elaine's account is also 8% annually, but it says it's compounded quarterly. What does that mean? It means that when you take a look at an entire calendar year, she gets 8% per year, but compounded quarterly means it's split up into 4 pieces. She's not going to get 8% 4 times. She's going to get 2% here, 2% here, 2% here, 2% here. which means when we start looking at the parameters, A equals, B equals, P equals, A is still $10,000, but B is not 1.08, it's 1.02. Because every time she gets interest, she gets 2%. It's just happening more often than Jerry's 8%. What is the period of time that she has to wait before she gets interest? A quarter of a year, 0.25 years. Perfect. So putting those parameters into this formula, y is equal to the original amount times 1.02 raised to the t over 0.25. So if we want to know how much money is in her account after 14 years, we can put 14 in for t. And solve that. So I would probably take 14 divided by 0.25 first. Then raise that as a power of 1.2 and multiply by 10,000. You can do it all in one shot on your calculator, certainly. 14 divided by 0.25 is 56, I believe. 1.02 raised to the 56 is that times the 10,000, which is telling us that the money in her account after 14 years is $30,311.65. And the amount of interest earned by her account would be that number minus 10,000. Does that make sense? Okay. We have one more example to do. How long would it take each of their investments to reach 40,000? So I'm not sure you have to write this down because you already have the formulas. Jerry's money is valued at 10,000 times 1.08 raised to the t, and we want this to be 40,000. Elaine's is 40,000 is going to be equal to 10,000 times, didn't leave myself enough room here, times 1.02 raised to the t over 0.25. So you have to solve each of these equations, but you don't know how to solve them algebraically, which means you have to solve them graphically. I'll do Elaine's first. I'm going to enter y equals 40,000 and y equals 10,000 multiplied by 1.02 raised to, in brackets, x divided by 0.25, closing all of my brackets. Think about this for a second. Elaine's investment starts at 10,000 and it goes up. I don't know what the answer is going to be, but I do know that I have to go up to at least 40,000, and I'm going to go up to 45,000. You know what you could do at this point in time in order to see what kind of domain you should be considering is you could set up your table to start at 0 and go up by 1. this will allow you to track her investment in the table. Well, it's going to be somewhere between 17 and 18 years. So in my window setting, I should go up to maybe 20. So there's the 40,000. Here comes Elaine's investment. Can find the intersection point and get 17.501. Now, years. I'm going to write down what the answer is and ask you to think about why I rounded the way I did. The answer is 17.75 years. Why didn't I just round it to 17.5 or 17.6? Right, and she's getting interest every quarter. So she gets interest at 0.0, 0.25, 0.5, which is the half point, and 0.75. So if we said 0.5, we said 17.5, she would not have that $40,000 yet. If we said 17.6, she wouldn't have that $40,000 yet. We have to go to the end of the quarter, which is 17.75. I think you get the gist. I think you could find the answer to Jerry's problem as well. Except there you would round up to the next year, because Jerry's getting money annually.